Okay, so today we're going to be starting chapter 18. Chapter 18 deals with two important chemical concepts. First, it deals with reaction rates, and then secondly, chemical equilibrium. Today we're going to be talking about reaction rates. So if you think about what a rate is a measure of how fast or slow something happens. Any change that is occurring will have a rate. So it's change per unit of time. So here we have four different events that are occurring, and what I'd like you to do is to arrange these events by rate, which is the fastest and which is the slowest. And any chemical reaction is going to have its own natural rate, and what we've learned to do as chemists is we've learned to affect certain variables to either speed up the reaction or slow it down. So I would say the fastest reaction is this fire here. And then the next fastest would be the sprint race, and then the reading of a book to a grandchild, and the ripening of fruit. Okay, so to explain reaction rates, we use what's called the collision theory. And if you remember, all particles are in constant random motion. Okay, so it's natural that if they're in the same vessel, they're going to collide with each other. But that doesn't mean they're going to react. In order to react, they have to collide with sufficient energy. But not only sufficient energy, they have to have proper orientation. So this diagram here illustrates both of those things happening. Here we have reactants that are moving too slowly. So they merely bounce off one another and no reaction occurs. Here we have reactants that are moving fast enough, but they're not facing the right way. So in order for the chemicals to react in this reaction, the carbon has to bump into the nitrogen compound. So there's not proper orientation here. So here there's sufficient energy and the proper orientation, so the chemicals collide and end up reacting. Now, there's a lot more going on in most chemical reactions than people realize. It's not just a matter of chemicals colliding. There's often intermediate steps that occur in just a nanosecond. So oftentimes there's something called an activated complex that is produced. An activated complex is defined as a momentarily temporary complex of molecules or atoms at the peak of the activation energy. So it's what's called a transition state. So a transition state is a transition between what? Well, between reactants and products. Okay, so here we have kind of this conglomeration, this activated complex that ends up leading to reactants. And here we have an activated complex that leads back to reactants. Okay, so the activated complex doesn't always end up in products. So what does it take to end up in products? Well, it takes sufficient kinetic energy and the proper orientation. So here we see that they're not oriented properly. You need two of these molecules on each of these in order to get product. And here, both sets are on the same one. Okay. So here we're seeing the production of water, probably. 2 hydrogens per oxygen. And here we're getting all 4 hydrogens on 1 oxygen. Okay, another thing that happens is that in order for a reaction to go, there has to be kind of a startup of energy. It needs a push. There's an energy hill that has to happen in order for the activated complex to form properly. So we call that the activation energy. The minimum amount of energy that colliding particles must have in order to react, in order to form an activated complex with sufficient energy. Okay. So if they collide and form an activated complex that doesn't have proper orientation and sufficient energy, then they just form right back to reactants. Okay, to illustrate this, I have a little toy. Okay, it's a rather complex toy, and if you just toss it up in the air, you see, oh my goodness, it changes colors. Tossing it up in the air. But sometimes you toss it and it doesn't change colors. Okay. So not all collisions produce products. So to show you how this works, see that there's a lot of complex interactions between the different parts of this toy. So this transition right here would be the activated complex, and this would be reactants, this would be products. Okay. So every chemical reaction has its own natural rate. Some reactions are naturally fast, like combustion, explosions. Some are naturally slow, like the working of a battery and the digestion of food. And then there are certain things we can do to either speed them up or slow them down. So first thing we can do is affect the concentration. So concentration, usually, if the concentration goes up, then the reaction rate goes up. We've seen this all year long when we did the flame test for the testing of the presence of oxygen. So here's an ember on a wood splint that's just glowing because of the 20% oxygen that's in the atmosphere. And then here's a gas bottle that has 100% oxygen in it. And you can see that if you put the splint in pure oxygen, then the rate of combustion increases significantly. Here's the combustion of steel wool, just in air, and here's the combustion of steel wool in pure oxygen. So the rate naturally goes up. So you might think to yourself, why would the rate go up? Well, think about the collisions. So in a lower concentration, there's going to be fewer collisions. The next factor that affects reaction rate is temperature. Okay, so generally speaking, if you increase the temperature of a reaction, then the rate is going to increase. Now, with collision theory, if you think about collisions, if you're walking to your next class, then there aren't going to be very many collisions. But if you're running to your next class, there's going to be a lot more collisions. So if you think about collision theory, the faster the collisions, the more likely they are to have sufficient energy in order for the reaction to occur. The next is particle size. Usually speaking, the particle size, as it gets smaller, the reaction rate increases. So if you think about a lump of coal versus black powder, which is merely coal ground into a fine powder, how much of this coal, if you put it in a fire, can actually react with the air? And it's just the surface, right? But if you grind it into a fine powder, every one of those particles is able to react. So gunpowder will react a lot more quickly than coal will. Think about why you chew your food. You chew your food not just to be able to swallow it, but so that it digests more quickly. Okay, and then the next is a catalyst. And as we learned earlier in the year, a catalyst is a substance that can increase the rate of reaction without being used up in the reaction. So the way it does this is it lowers the activation energy. So with a catalyst, it takes less energy for the reaction to take place. And it does this by making it easier for the molecules to interact with proper orientation. So a catalyst is kind of like a go-between. A good illustration would be like a tugboat. If you have a big ship that has to dock in a dock, it's going to be very difficult to turn and orient properly. But if you have a tugboat, they're able to push and line up the ship to get it to dock properly. Now, in natural systems, there are biological catalysts, and we call those biological catalysts enzymes. Okay, so digestion takes a long time, but it would take even longer without enzymes, without digestive enzymes that speed up the process. Then there are also biological substances that block the action of enzymes, and they're called inhibitors. And inhibitors will dock to the place that enzymes usually dock preventing the enzyme from doing its thing. So the net effect is that an inhibitor will essentially slow down a reaction, or it seems to slow down a reaction, but really all it does is it blocks the action of the enzyme. Now, if you think about food spoilage as a chemical reaction that is um, negative for human life, there are certain things we can do to slow down the rate of food spoilage. Now, what is it that causes food to spoil? And generally speaking, it's the action of bacteria. And sometimes it's just the action of oxygen with the foodstuffs. So when we put food into a refrigerator, what does it do? Well, it slows down the rate of bacterial growth so that bacteria can't grow as fast. If we freeze food, it doesn't kill the bacteria, it just slows down the rate even more. Another thing we can do is add preservatives. Preservatives are chemicals that do one of two things. One, they can um, they can be like antibiotics, antimicrobials that actually will kill the bacteria, and thereby making the food last longer. Or they can be antioxidants, which slow down the rate of um, making food stale. So if you've ever tasted old cereal or old crackers and they taste kind of like cardboard, it's because they're stale. They're not going to make you sick. They haven't spoiled like this would, but they've just kind of gotten stale. Another thing we can do is make airtight packaging so that if there's no oxygen in there, nothing can grow.